All right, take it away.
All right, I'm on. All right. Hey guys, my name is Deepak from the product team at NeuroBlade. And before I start, I am very quickly going to click submit on this query and see I'm connected to my Presto cluster. And what I have done is I have run this morning, I think Krishna was speaking about fuzzers. I ran this query, which runs on the CPU. Come on. And now I'm going to take the same query and I'm going to run it on our dedicated processor called the SPU. So let that run. And if I time this right, it will be done by the time I reach the slide. Right. So this is what I'm here to talk about. This little guy, it's a PCIe card that we make called the SPU, or the SQL Processing Unit. At the heart of this card is a processor that we built, pretty unimaginatively called the SPU processor, and it's purpose built for analytics. It's a PCIe card that you stick into a compute node, so it fits in any compute node that has a PCIe slot. And once it's in, what it does is it starts offloading the CPU on the worker node. So operations that were running on the CPU start running on our dedicated processor. Now, nothing works by magic, so we've had to build integrations. And we have an API and an integration model. And to prove that this works, we have done an integration with Presto, which we're going to talk about. We've also done integrations with ClickHouse, with Spark. And some customers have taken our API and built them into their own high-performance computing applications. Right? So any of those flavors is possible. Okay, so what I'm connected to is I'm connected to a Presto cluster running a stock open source coordinator. Haven't touched it. And there are 4 worker nodes. The worker nodes obviously have some CPU, some memory, and some disk. But the worker nodes also have our card in them, which is the SPU. Now, what we can do is we can, through software, either enable or disable the card. So the same worker nodes run the work CPU query, which is running stock Prestissimo, or the SPU query, which is running NeuroBlade enhanced Prestissimo, so Velox plus NeuroBlade. And the data sits on object storage, just like it does in a real cluster. And we're done, right? So the query finished. And you can see, let's do it this way. When the query ran in the CPU, it ran around 6 minutes. And when it ran on the SPU, it ran in less than around a minute and a half, 1.75 minutes. And that's what I want to talk about for the rest of the talk. So to make my life easier, to avoid switching, I took some screenshots a little while earlier. So on the top is the query running on the CPU. You can see in this one, it ran 5.71 minutes. We're all in that range. And it ran on the SPU in 1.37 minutes, so a little faster than it ran right now. Okay, but that's just a small difference, because what we see is once we enable the SPU, the query ran roughly 4 times faster than it did. Okay, and if you're a little bit of a skeptic, you're going to say, "Hey, dummy, it's a distributed system. I could get the same thing. I can just throw more CPU and more memory at the problem." That's how we built it. We built it to scale, and the answer is yes, of course, but that's not the only thing this system is doing, right? We're not just making the query faster. The question is, can the SPU pay for itself by reducing your reliance on those other resources? Can we do more with less? So what we do here, and these are from the Presto UI, so they're rough numbers. We have more finer grained numbers than this, but what we're seeing is memory utilization is dropping rather significantly, and CPU utilization is dropping significantly as well. So in this query, once the SPU is enabled, we're taking about 1/3 the CPU that we were before. And I don't even know, 1/10 or less of the memory that we were taking before, right? And I want to talk to you about what the SPU does that makes this happen. Okay. So SQL has been around, it's definitely longer than I have been around, right? It's a very, very mature ecosystem. And when we looked at accelerating something like SQL, we had to really dig deep and start at first principles. And in the database world, the first principle is scan. every query starts with a scan. You read the data from disk. Now, if you're looking from the query coordinator, it looks like one operation. But if you look at it from the CPU side, it's not. It's multiple operations. The data has to be read. It's almost always decompressed, or compressor needs to be decompressed. Then it's encoded. And finally, it's still on disk in disk format and serialized format. It needs to be written to memory. So it needs to be deserialized. And from a CPU perspective, each of those operations is a distinct operation. Each of those operations requires round trips to memory. So CPUs have become bigger, wider, faster. SIMD has been invented. But at the end of the day, all those memory operations add up. They create latency, which makes scan a very expensive operation. So that was the first thing we set out to improve, right? So what we've done is on our custom processor, we have engines. We have engines that do the read, that do the decompress, that do the decode, that do the serialize. And all these engines work in a pipeline. There are multiple copies of each engine, but they all work in a pipeline. So we're reading data, we're right on the bus, we're reading data at PCIe speed. And as this data is making its way through the processor, these engines are working on it and it's being read, decompressed, decoded, and deserialized and written out to host memory. Okay, so from a storage perspective, we're reading at PCIe speed. So whatever your PCIe generation is, we can drive the hardware at that speed. From a table format perspective, we understand major table formats. Today we're going to be talking about Hive, but we can understand the table formats as well. And what's also important is what's happening on the other side, right? We're trying to write the data out back to the CPU in a memory format that the database can consume immediately. Right? So our default is Arrow, which works for Presto. But for ClickHouse, we had to go to ClickHouse native format, for example. But what happens is once we read the data and we write it to memory, it's now ready for use by the database without any transcoding, without any transformation. Right? Some of our customers call this zero copy because that becomes the memory that they use for the rest of the operations. They don't have to copy it elsewhere into another buffer to transform it. Okay, so as I mentioned, we're reading the data and it's running through a system at PCIe speed. That was the very beginning. Then the smart guys in engineering said, well, as this data is moving through the system, what else can we do to it, right? So we started pushing down more operations. You can take a filter operation and you can apply it to the data as it's streaming through the system. You can take a project operation, you can apply it to the data as it's streaming through the system. And those are the basic operations. We can do more. We've added support for partial aggregations. We can do many kinds of local joins. And what's important is all of this is being processed through the system at PCIe speeds. It's all inline processing as it's moving through the system. And at the end, what you get is you get this database readable memory copy, right? So zero copy in memory, which you can use to perform the rest of the database operations on it. Okay, so what does this mean for a SQL query? So on the left, I've written down a SQL query, and as it makes its way through the system, it goes to the coordinator, to the optimizer, it gets transformed into tasks. We don't touch any of that. And finally, you create an execution plan that goes down to the worker, right? As I kept saying before, SQL is a massive set of operations, right? Where our hardware is evolving. We're not yet SQL complete, but our system is SQL complete, and that's what I want to talk about, right? So what happens is our software can look at an execution plan, and it can come back and through the API tell you, well, this bits of the execution plan, those can be done on the CPU, on the SPU. The other bits, the SPU is not ready for yet. So why don't you execute them on the CPU, right? So I call it the better together model. So the way we achieve query completeness is each execution plan is broken into two parts. One, which we call the SPU part, is the worker pushes that down to the SPU. And the rest of it, which is stuff the SPU can't handle, those get executed on the CPU as normal. Right? And all of this is aligned to the way Presto Worker works. So it's aligned to the split model. Each worker reads that little sliver of data that it needs to, understands what parts it can push down to the SPU, understands what parts needs to be executed to the CPU, and then data is sent out as splits. And this operation keeps continuing. Each worker keeps adding splits until it's done processing. And then it says end of splits, and that's when the final result is computed and sent back up to the next operation in the line. Okay, so what we're announcing today, what we're launching today, we've had it for some time, but just what I'm talking about today is what is the physical manifestation for it, right? So what we've done is we've worked with Velox to modify it so that it understands natively the SPU, right? And we've released it as a modified Hive connector. So we call it the NB Hive connector. From the you just switch your catalog to the NB Hive catalog, and that is the trigger that you need for the workers to understand that now they need to start taking the execution plan, and they need to start using our API to parse it and to break it up into SPU parts and offload them to the SPU and run the CPU parts on the CPU. It's a very non-intrusive system in the sense that we don't touch the coordinator. There's no change to data formats. There's no change to file locations. Every worker gets the same execution plan as it did before. Nothing changes. The only thing that changes is at runtime. Each worker is making runtime decisions about what gets pushed down to the SPU and what is the remainder that gets executed on the CPU. And I showed you a query. I picked an arbitrary query that worked with so that it executed in exactly the time it took me to go through 2 slides. You saw a 4x speed up, but what we see in a well-performant, well-engineered system is about an 8 to 12x speed up in performance. And that comes with a significant cost savings because we're reducing the reliance on memory. We're reducing the reliance on CPU. So you can do more with less. You can run bigger queries with the same resources you have or buy less resources. And that, roughly speaking, improves the deployment efficiency by a factor of 20. So these are results that we've computed on TPCH 10 terabytes. We've seen similar results on other sizes and TPCDS as well. So with that being said, if you click on that QR code, it takes you to our contact us page. Please reach out to us. Our software is ready, it's available. We're happy to share it with you. What you need is you need to get a POC kit. You need to get one of these cards from us, stick it in a server, and then you have 2 choices to make. You can either get our SDK, which is a C++ SDK. We lovingly call it DAXL for data acceleration, and you can build your own integration. Or we're happy to share our reference implementations with you. We can give you containers that contain a full-fledged worker. We can share source code with you, and there's multiple ways of working with us. Today we have fully available integration with Presto and ClickHouse. We've also done an integration with Spark that we can share with you, but the full-fledged release is going to come a little bit later in the roadmap. And the card is available. You can buy it from us. You can buy it from an OEM. We're happy to work with your ODM as well to stick it into your server. And we have a compatibility list of servers that we work with. So that's the end of what I wanted to say. Please, I invite you to click on that or take a picture of that QR code and reach out to us. And happy to answer any questions. All right. Thanks, guys.
Okay, go ahead. Yeah.